Okay, guys, looks like the quiz should be timed out for everybody. Just a couple of things to mention to you along the way that hopefully will make your life a little easier as you delve into the newer stuff we're going to be doing with Chem 101. When we start dealing with reaction equations, and by the way, I also opened up chapter 4 homework for those of you who want to go ahead and get started with it. So that starts with balancing the reaction equations. This is one of those situations where it pays to definitely practice a little in Chem 101 because it gets kind of format picky. So as I mentioned during the quiz, I think this is one of those ones where you just had to pretty much throw the coefficients into an already existing reaction in there. But sometimes you actually have to write out the reaction in Chem 101. And I can tell you that Chem 101 likes to see the states. Okay, so when I say the states, I'm talking about whether something is a solid, aqueous, liquid, gas. Make sure you put those in there because if you don't, Chem 101 will mark your answer wrong. So it seems like a really minor thing, but it's just something that Chem 101 is picky about. So I just like to bring that to your attention, and that's why it's important to just play around with these things, during in-class practice and during homework, so you know that going into it in a quiz. All right, so just be aware of that. All right, so let me go ahead and pick up with balancing reaction equations. And we're just going to do one or two here real quick, just to kind of review what we were talking about back in the video. And then we're going to talk about an application of this that we're going to be using pretty much throughout the entirety of the course. All right, so let's just throw another reaction equation down here. And this is another typical one that you might see. Ag2SO4. So that would be what? Silver 1 sulfate. I better put my AQ there. That's a soluble salt. Let that react with barium iodide. That's BaI2. That's also soluble. And we end up making barium sulfate. That's a solid. So we write that down. And I also end up making silver 1 iodide, which is AgI. Okay. And we're actually going to get into, and that's a solid as well. All right. So when we actually start writing chemical reaction equations and we start talking about types of reactions equations, which comes up pretty soon, we'll go back and make sure that we can remember how to get between formulas and names for ionic type compounds such as this. Okay, so sometimes these could be given to you as names, and you have to go from names back to formulas before you can actually do the balancing. Now, the trick I wanted to mention on something like this is you can see that you've got a sulfate in here, right? So that's polyatomic ion. Now, the nice thing about this from a balancing perspective is that you notice that it's sulfate on both sides of the equation. So if I see something that's not changing its chemical form from one side to the other, I'm just going to balance it as sulfates instead of picking it apart into sulfurs and oxygens. Okay, it just makes it easier that way. Okay, so I'm going to balance as sulfate. So be aware of that when you go about balancing reaction equations. So let's start with the silver on the left-hand side. Notice that I've got 2 atoms of silver over there, but I've only got 1 atom of silver on the right-hand side. So again, what I'm going to do is I'm going to put a coefficient 2 in front. And that's another thing that students sometimes do, and you got to be watching out for, is whenever we balance a reaction equation, use coefficients out front, okay? Don't mess with subscripts. Sometimes students like to balance equations by messing with subscripts. So in other words, I've seen situations where somebody might have tried to balance that silver on the right by making it Ag2I instead of 2AgI, okay? If I make it Ag2I, I just change the identity of the molecule, okay? And I can't do that. All right, so sulfates, that's next. Looks like I got 1 sulfate on the left. I got 1 sulfate on the right. Sulfates look good. Barium's next. Okay, I've got 1 barium on the left, 1 barium on the right. We're good. Iodine is next. It looks like we've got 2 I's on the left. Oh, and if I distribute that 2 through on the right, I've got 2 iodides there as well. So it looks like they work out. Okay, so I've got a balanced reaction equation. This one was easy, but I just wanted to make sure you guys were aware that we could compare sulfates to sulfates on both sides of the equation. That just keeps things simpler. Okay, and we'll see that a lot as we go. All right, so let's now kind of do the next thing that we want to talk about here. I think most folks here are pretty good at balancing equations, and we'll practice more with that here in Chem 101 a little bit later, again, to get you used to sort of the formatting that Chem 101 likes to see. But now what I want to talk about is stoichiometric relationships. I'll tell you what that means here in just a bit. Okay, so let's just start out with a reaction equation, and we can balance it just to get a little more practice. So we've got potassium chlorate, that's ClO3, KClO3, that's a solid. And we're going to let that decompose with heat. And when I take solid potassium chloride and I let it come apart in heat, I make potassium chloride, which is KCl. It's also a solid. And I make some oxygen. That's a gas. All right, so at this point, we ought to be able to try to balance this thing out. One potassium on the left, one potassium on the right. Looks like I've got one chlorine on the left, one chlorine on the right. 3 oxygens on the left, but only 2 oxygens on the right. So what I could do here is I could kind of break this down into 2 steps. I could do this by putting a 3/2 out in front of the O2 here. And when you multiply that, you'll see that you get 3 oxygens out on the right to balance the 3 oxygens on the left. The 2 and the 2 cancel, right? But now we know that we don't want fractional coefficients. So like in one of the examples we saw in the video, I can get rid of that by multiplying everything through by 2. Okay, so now to make whole numbers out of this, I'm going to make 2 KClO3 solids. Okay, and that's going to go to 2 potassium chlorides, KCl, that's also a solid. And now multiplying through, the 2's cancel, and I have 3 O2s. And that's a gas. Okay, so now it looks like I've got 2 potassiums on the left, 2 potassiums on the right, 2 chlorines on the left, 2 chlorines on the right, 6 oxygens on the left, and 6 oxygens on the right. So that's how I do it with whole number coefficients. Okay, so I got a balanced reaction.
What is KCl?
What is KCl?
What's the state of KCl?
It's a solid. And the reason why, if you go back and you think about it, you might say, but wait a minute, isn't KCl one of those things that you learn with your solubility rules, which we haven't done yet, is actually soluble? Well, if you put it in an aqueous solution, it is. But in this case, we're just decomposing solid potassium chlorate, okay? And when you do that, you make potassium chloride, which is still a solid, still a crystalline solid, and oxygen gas. All right, so here's the situation when we deal with stoichiometric relationships. What if, let's say, for example, I know I'm going to start out with 32.8 grams of the potassium chlorate. And the question I might ask myself is, okay, how many moles? Let's just do it in terms of moles. I could do it in terms of grams, moles, number of molecules, whatever. But what if I wanted to know how many moles of oxygen gas I could make if I decomposed all 32.8 grams of my KClO3? Could I do that? Could I figure that out, assuming the reaction goes 100% to the right? Yeah, and this is what I mean by stoichiometric relationships. What I can do is take knowledge of some species in the balanced chemical reaction equation, and I can relate that through the balanced chemical reaction equation to some other species that I want to know about that I don't now know about, okay? So in other words, if I have information about the KClO3, I should be able to now determine how much oxygen I can make, okay? So it comes down to relating things in a balanced chemical reaction equation. Now, why can I do that? Well, let's go back to the video and just sort of remember a couple of things we said about balanced chemical reaction equations. There's really 2 ways I could think about this. I could say, for example, over here on the left, that for every 2 molecules of the KClO3 that I use up, I'm going to make 2 molecules of the KCl, and I'm going to make 3 molecules of the water, or sorry, of the oxygen. Okay, so notice that the coefficients just drop down. Okay, so for every 2 molecules of KClO3 I lose, the balanced chemical reaction equation tells me I'm going to make 3 molecules of O2. Everybody see that? Now, if I can do this in terms of molecules, I can talk about it also in terms of moles, right? So remember, the mole lets us scale things up to a reasonable size that we can measure out. I can't measure out 2 molecules of KClO3, okay? But I can measure out 2 moles of it, right? Because I know, of course, how many things are in a mole. And that makes that a manageable quantity for me. So alternatively, I can say that 2 moles of KClO3 when it reacts will give me 2 moles of KCl and also 3 moles of oxygen. So now I can establish this thing that we sometimes call a mole bridge, which is just a conversion factor. So it's going to take us from the moles of the thing that we know about, which in this case is the KClO3, and I can relate that back through the balanced chemical equation to the moles of the O2 that I want to find out about. Okay, so it's just a way of establishing another conversion factor. We've already kind of sort of done this when we talked about, for example, pulling out parts of molecules, right? So if I had like C2O4 or something like that, and I wanted to some mole amount of it, and I wanted to figure out how many moles of carbon are in it, I could do that by just saying, okay, for every 1 molecule of the C2O4, I've got 2 moles of carbon. So it's a similar kind of thing to that, which we've already done before. Okay, so let's go ahead and see if we can solve our original problem. All right, so my given here is going to be 32.8 grams of KClO3. Okay, now remember, the mole is going to be our central unit. We always work through the mole, and this is why. Because I can't directly talk about grams of KClO3 and relate that to grams of KCl or grams of oxygen. I got to go through the mole because that is what the balanced chemical equation, its coefficients refer to. Okay, so what I need to do first is convert my mass of KClO3 to my moles of KClO3. So at this point, it's kind of like a any other kind of problem like this that we work, where we've done ones like this when we talked about, say, empirical formula, where we had to go from grams to moles of something. Okay, same thing. All right, so for every 1 mole of KClO3, the periodic table will tell me, based on the molar mass, what the mass of 1 mole is. So I went back and did that. And 1 mole of KClO3 corresponds to a mass of 122.55 grams of the compound. Okay, so grams cancel with grams, leaving me with moles of KClO3. Once I'm in terms of moles, now I can establish my so-called mole bridge. Okay, so if you go back up and look at the balanced equations, I can start from the point of view of the thing that I want, and I can make this bridge over to the thing that I'm trying to find out about, which is the oxygen. And I can do that by establishing a mole ratio. All right. So again, this is not that different from saying, okay, in 1 mole of CO2, I've got 1 mole of carbon or 2 moles of oxygen. It's the very same thing. Only now I'm relating things in a balanced reaction equation. So I want to get rid of the KClO3. So I know I have to have moles of KClO3 in the bottom. And I'm trying to get to moles of oxygen. So that's got to be in the top. Okay, so now we need that actual mole ratio, which just comes from the stoichiometric coefficients. Those are the numbers out in front, right? So if you look up at the balanced reaction equation, note that for every 3 moles of O2, I'm using up 2 moles of the potassium chlorate. Everybody see that from the balanced reaction equation? Okay, any questions so far? Okay, good. So now notice what happens. Your moles of your KClO3 cancel with your moles of KClO3. I'm left with my moles of O2. That's what I want. Okay, so now I can work this through and get the right number of sig figs. And I get 0.401 moles. And that's of oxygen gas, okay? So everybody more or less see what we did there? Now, let's cast this in a little bit different light here. Try something else. I'm going to use the same balanced reaction, so let me go ahead and rewrite it down here so things don't get too busy. Let's say, for example, in this situation, I actually ran the reaction, right? And when I ran the reaction, I collected and weighed out 28.3 grams of O2. So I captured the oxygen and weighed it, okay? And I got 28.3 grams of it when the reaction came to completion, all right? So the question is, how many grams of KCl did I form in that reaction? Okay, so notice in this case, I don't give you any information about the reactant, the thing over on the right-hand side of the equation, or sorry, on the left-hand side of the equation. Everything is in terms of products, which is everything to the right of the arrow. So if I have knowledge of one product, can I get back to information about the other product? In other words, if I didn't just weigh out the grams of KCl that I made, could I actually then determine it from the mass of the oxygen that I say collected in a trap? Could I do that? And the answer is yes. It's the very same process, right? So basically what we're going to do is we're just going to start with the grams of the oxygen because that's what's given to us. Okay. Now we always go from grams to where?
Moles.
Moles, yeah, that's it. You got to go to those moles. Very good. You'll hear that again and again and again. Okay, so for every 1 mole of O2, okay, we end up having about 32.00 grams of O2. That's a 32 down there, guys. Okay. Now, notice what happens. Grams of O2 cancel with grams of O2. So now what I can do is I can establish my mole bridge again. But the nice thing about a mole bridge is I can establish a mole bridge between any two things in a balanced chemical reaction equation. It doesn't have to be just between a reactant and a product or a product back to a reactant. In this case, I can establish a mole bridge between a product and another product. Okay. All I need is a balanced reaction equation, and I can relate anything in that balanced reaction equation to anything else in that balanced reaction equation. Doesn't matter what it is. Okay, so now I'm going to establish my conversion factor here. So I know I want to get rid of moles of O2, so that has to be on the bottom. And I want to get to moles of KCl because that's what's going to be on the top, and that's what I'm looking for. Okay, so notice for every 3 moles of O2 that I make, I'm also making 2 moles of KCl. Again, the balanced reaction equation tells me that. Okay, so now moles of O2 should cancel with moles of O2. I'm moving in the right direction now because now I've got information about the thing I'm looking for. I've got it in terms of moles. But now I got to take it to grams, but that's easy. Hey, I know how to do that, right? If I've got moles, I know how to get from moles of something to grams of something. I know that for every 1 mole of KCl, the periodic table tells me, based on the molar mass, that I'm going to have 74.5513 grams of KCl. Okay, that's the molar mass of it. Okay, so notice what happens. Moles of KCl cancel with moles of KCl. Now I can go ahead and work this thing out. And it looks like I'm going to be good to what, 3 sig figs here based on the 28.3 grams of O2. And I get 44.0 grams of KCl that I make in the reaction equation. And I could have done this the other way. What if I had the mass of the KCl? Because that's an easy thing to weigh out, but I couldn't trap the oxygen, and I wanted to know what the mass of the oxygen was. I could do it the very same way. I would just work my mole bridge in the opposite direction, going from the KCl to the O2. Okay? All right, everybody good with that? So that's kind of our introduction to stoichiometry or stoichiometric relationships. And you're going to hear that a lot because one of the big things we're going to do pretty much from here on out in the course is exactly this: use a balanced chemical reaction equation to get from one species that we know about to another species that we want to find out about. All right, any questions in general about that before I move on? Not too hard, right? Now, I'm going to put another fly in the ointment here, and this is something that is going to kind of begin our discussion for the next video. And it's a really, really important topic. So I just kind of want to introduce it here, okay? So the nice thing about this reaction equation that I did here is there's only one reactant, right? So if I start out with some amount of KClO3, there's really only one way this reaction can go, and that's left to right. And there's only one reactant to use up. But what about a situation such as this? I think this is actually the example I do in the video. I may be wrong about that, but let's take this one, for example. I've got magnesium, solid. This is actually kind of a neat reaction if you've ever seen it. It's the burning of magnesium. So it reacts with oxygen gas, and basically you can spark this or set fire to a strip of magnesium, and it burns with a very, very intense bluish white glow. As a matter of fact, in the military, they make flares out of those. And you end up making solid magnesium oxide. That's MgO. Okay. Now, you can balance this by inspection. It's not hard to do. One magnesium on the left. We got one magnesium on the right. Oh, but we got two oxygens on the left, but only one on the right. So I'm going to use a coefficient out front to fix that. But now notice I've got two magnesiums on the right, so I need to adjust on the left by putting a 2 out front. Okay, so that's a fairly easy one to balance. Now, here's the deal. Notice in this case that I've got two reactants. I've got magnesium and I've got oxygen. Okay, so if I were just going to do this, let's just say, for example, I've got 10 grams of magnesium. Okay, and I just let it burn. All right. We should be able to predict the mass of the magnesium oxide that we're going to make on the right. Okay, it shouldn't be hard to do that. Now, what's the assumption I'm making when I do that? So in other words, I want to get some number of grams of magnesium oxide over here. Okay, I can still establish a mole bridge, right? Just like I did before. And I could convert my 10 grams of magnesium over to moles of magnesium and then use my mole bridge between the two, right, to get to moles of magnesium oxide. Notice it's 2-for-2 ratio there. And then once I have the moles of magnesium oxide, I could easily take that over to grams of magnesium oxide. But what have I not considered here?
If you have enough oxygen?
Yeah, it's the oxygen. I got another reactant I got to worry about here, right? So now this thing, this oxygen, turns out to be an issue. Now, in the real world, if I were just doing this in the open air, would I need to worry about the oxygen in terms of how much of it I've got? Probably not, because I'm going to have way, way more than I need, right? If I'm just doing this in the open air, I've got limitless amounts of oxygen that I can use, okay? So the assumption here is that in air, the oxygen would be considered what we call an excess reactant, okay? We're never going to run out of it. All right, but here's the deal. The magnesium in this case would become what we call the limiting reactant. Why do I call it limiting? Well, I call it limiting because that's the one I'm going to run out of, okay? I'm going to run out of the magnesium before I run out of the oxygen because I got way more oxygen than I'll ever need because it's present in the air. As long as I've got air surrounding the magnesium, I've got oxygen. So the one I'm going to run out of is going to ultimately be the magnesium, okay? So when we try to determine how much of the MgO that we make, we always have to do it based upon the reactant we're going to run out of first, right? Because once we run out of the magnesium, can the reaction continue to go? No, it can't, right? There's no more reactant to use up. So I've made as much MgO as I possibly can based on the amount of magnesium that I've got, okay? But what would happen if I actually ran this in a closed container and I introduced some amount of O2 into that container, okay? Now at this point, depending on how much of the O2 I put in, it may not be the excess reactant anymore. Maybe I'll run out of it first, right? And if I run out of the oxygen first, then that quantity is going to dictate how much MgO I can make, and I would have some Mg left over, okay? You kind of see the problem that we have to deal with here when we end up with two or more reactants or two or more things on the left-hand side of the arrow. You know, now I got to worry about which one of them I'm going to run out of first, because that one is going to dictate the amount of product that I'm going to make. Does that make sense to everybody? It's kind of like making a sandwich, right? If you want to make a sandwich with bread, meat, and cheese, right? You need to have per sandwich 2 pieces of bread, 1 piece of meat, and 1 piece of cheese, right? And you're going to go make a bunch of sandwiches for, say, a church picnic or something like that, okay? What's going to dictate how many sandwiches you can make? What's going to limit you? Well, you're obviously going to be limited by whichever of those ingredients you're going to have the least amount of. Okay, so let's say you want to make a certain number of sandwiches, but you've got, say, 50 pieces of bread and you got 30 pieces of meat, but you only got 10 pieces of cheese. How many sandwiches are you going to make?
10.
Yeah, you're going to make 10 sandwiches because you can keep making them until you run out of cheese and then you're done, right? Unless you want to just make meat and bread sandwiches, which is fine too. If you're hungry enough, that's what you'll eat. Okay, but you get the idea. It's the very same thing going on here in a chemical reaction as it would be in terms of making sandwiches. Okay, it's the very same problem. We have to then be able to identify which reactant we're going to run out of so we can then determine how much product we can make. Okay, and that's ultimately where we're going to go with our next video. But I wanted to introduce the topic here because it's a really, really important topic. And sometimes getting into those calculations can be a little bit difficult for students. So if you have a really good grasp on what it is we're trying to do here, hopefully it'll make the calculations a little easier when we start getting into them. All right, so let's go ahead over to Chem 101 and do some practice with just balancing reaction equations. There's no stoichiometry over there or anything like that in this case. We just want to get you used to formatting out and balancing chemical reaction equations in Chem 101. All right, so let's just pop out of here for a minute. We're going to go back to Chem 101, wherever that is. There it is. I can do it from here as well. It's probably easier from my desktop to do it. Although we can look at it here together this way. This is all the way over in chapter 4 here. All right, so there's a lot of stuff to do over here. Chemical reactions and balancing. We are off and running, guys. I'll go ahead and do it here so we can look at it together if need be. All right, so we got a whole bunch of them here for you to go look at. Here they are. And again, pay attention to formatting here, guys. Remember, Chem 101 likes to see the stoichiometric coefficients. And if you have to, it wants to see those states in there if you have to add them in there as well. I think that's true down here in the bottom couple. You have to kind of make your own. Oh, that first one's a combustion reaction. I think we did one of those in the video, didn't we?
Uh,
Yeah, go ahead.
Professor, could you do I believe on your screen it is, I believe, question 6.
Yeah, sure. We can do that one. Actually, let me bop off of the screen here so we can do it together. Let me go back to my notes here. Yeah, let's do that. That's a good one. I was kind of hoping you guys would ask for either 5 or 6, because that's a good one, because we have to actually go from a description to an actual reaction. Okay, so C7H8, they give us that one. Oh, and they tell me that's a liquid, right? So I have to make sure I put a L after it. It says burned with oxygen gas. So that's a reactant. So I'm going to put an O2 there. That's a gas. Make sure you put the gas in there, right? And this is a standard combustion reaction where you're generating carbon dioxide, which is a gas. So that's CO2. Make sure you put the G in there. And water vapor. Now, what is the state of water vapor? What should I put after that? L or G?
Is that just not, yeah,
It's gas. Yeah. Whenever you see vapor, that just means a gas. Okay. So now that's a C7. It looks like a 3 there, but it's a 7. Okay. So now what we're going to do is we're going to do the regular thing. This is a combustion reaction. So this one gets a little tricky because it's oxygen is showing up in 2 places on the left. So really oxygen shows up in 4 places here. So that means we're going to deal with the carbons and the hydrogens first. Okay. So I got 7 carbons on the left. So the only place carbon appears is over on the right there in CO2. So we'll put a 7 there. Let's do the oxygens while we're here. Okay, so it looks like I got 8 on the left. I need 8 on the right. So what do I have to put in front of the H2O to make that happen?
is 4.
Yeah, you got it. You need a 4. Very good. So now let's tally up the number of oxygens we got here. Okay, so from carbon dioxide, I've got twice 7, which is 14, right? And then over here, it looks like I've got another 4, right? If I distribute through. So 14 and 4 tells me I've got 18 oxygens, right? Everybody see that? Now, watch out, because one of the oxygens of that 18 is coming from there, okay? So now that means I need 17 left coming from the O2. So the way I'm going to fix that is I'm going to put a 17 halves out in front there, right? So now I've got basically the 2 here times the 2, those cancel out, 2's in the top and the bottom. So that's 17 plus the extra one on the left there in the C7H8O. Okay, that gives me my 18 that I need. Okay, so now to get rid of the fraction, what I have to do is take this whole thing and multiply it through by 2. Okay, so that's going to give me 2 C7H8O. And remember, I need my L after that. The 2's just going to distribute through and cancel there to give me 17 O2s. Make sure you put the G after that. 2 times 7 is 14. Carbon dioxide. That's also a gas. Make sure that's in there. Plus twice 4 is 8 H2Os. And again, it's a vapor, so make sure you put the G in there. Okay, I think we got that one now. Does that make sense?
Yeah. Yeah,
Good.
it makes more sense now.
Excellent. Yeah, it's keeping track of the oxygens. The only hard part about that one is making sure the oxygens work. Excellent. That was a good one to do. I'm glad you asked about it. Okay, so it looks like we timed out on that. Just a couple reminders, guys. We got a Friday quiz coming up here, so make sure you're going back and looking over the stuff from the past week. And also, make sure you're practicing this stuff. Make sure you're used to being able to put those chemical reaction equations into Chem 101 and you're getting the right answer back out. I don't want you guys getting dinged on little things here. So make sure you're practiced up and you're doing that correctly. All right. If there are no other questions, folks, have a great rest of the day, and I will see you guys on Friday.
Thank you.
Thank you.